Hello guys, so far in the logic gates chapter we have covered these topics. In case if you miss, the link is available in the description. Today we will learn about controlled inverter and 4-bit adder subtractor. So let's start with controlled inverter. Here is the diagram of controlled inverter where a 8-bit register is used to store the 8 bit of Boolean word or numbers. So let's see how it works. A register is a group of devices that stores a binary number. The 8-bit register can store only 8-bit binary numbers or a word. Here it is a 8-bit register which is used to store 8-bit binary numbers from A0 to A7. An XOR gate produces a high output when its inputs are not the same, or we can say that having odd number of high inputs. Here is the truth table of XOR gate. When high inputs are in odd order, look at here, 1 is odd, here as well, we will get high output. And when all the inputs are low, output is low, or when there are even number of high inputs, output is low. So an alternative interpretation is to view XOR gate as controlled inverter. Now what is inverter? That means a NOT gate which gives one's complement of binary number. If I give 1 in the input, so at the output of inverter it will be 0. When inverter input is low, look at here, all the bits are passes through XOR gate and a inverter, a common input inverter which is passes through all the gates, all the XOR gates. That means for 2 input XOR gate we have one input is our one input is came from 8-bit register and another input is inverter. That means the value of output depends on the value of inverter. Now first condition, when inverter input is low, that means low means 0, so inverter input is low. Suppose my input A is equal to A7, A6, A5, A4, A3, A2, A1, A0, a 8-bit binary number, that is 11001011. That means what I get from here, A0 is equal to 1, A1 is equal to 1, A2 is equal to 0, A3 is equal to 1, A4 is equal to 0, A5 is equal to 0, A6 is equal to 1 and A7 is equal to 1. And my output Y is equal to Y7, Y6, Y4, Y3, Y2, Y1 and Y0. That is nothing but output of all the XOR gates. Clear? Now suppose I give this input from here is my input 11001011. Now it is stored in 8-bit register. Now it passes through the output terminal. They work as an input for XOR gate. So I took the A0 as inverter input is low, that is 0. So at this Y0 what will be the input? 1, that is A0, 1, and inverter is 0, low means 0, so 1 0. So when XOR, one input is 1, another is 0, A XOR B is 1. So what will I get? Output at Y0, 1. A1 is equal to 1, so 1 and 0, 1 and 0, output is 1. Here we go. Next 0 to this portion A2. Inverter is also 0. So 0 and 0 will give me output 0. Here it is, Y2 is 0. Then A3. A3 is 1. 1 and inverter 0. So 1 and 0 will give me 1. So here is y3 is equal to 1. Then a4 is equal to 0. So a4 is 0, inverter is 0. 0, 0. Output is 0. Here we go, y4 is 0. a5 is 0. So 0 and inverter 0. Output is 0. Here it is. a6 1, inverter is 0, so 1 0 1. a7 1, inverter is 0, 1 0 1. Here it is. So what I get from here, when the inverter input is low, output is same as input. Look at here, double 1 double 0 1 0 double 1 1 0 double 1. So when inverter input is low, output is same. Now what happens when inverter is high? When inverter input is high, it transmits one's complement of register word to the output. Now let's see. A0 is equal to 1. Inverter is high, that means 1. So at y0 or the first XOR gate, the inputs are 1 1 1 1. Output is 0. Here it is 0. Next is 1. A1 is 1, inverter is 1. So 1 1 0. Here it is. Next is 0 to the A2. Inverter is 1. So 0 and 1. 0 and 1 will give me 1. Then next is 1. Inverter is 1. 1 1 0. Here it is. Now next is 0. Inverter is 1. 0 1 1. Here it is. Again next is 0. Inverter is 1. 0 1 1. Here it is. Now next is 1. A6 is 1. Inverter is high. 1 1 0. Here it is. And A7 is also 1. Inverter is 1. So 1 1 0. So here when inverter input is high, that is 1, what we get? 0 0 1 1 0 1 0 0. That is one's complement of the input number. Now in this manner, an XOR gate can be used as inverter. So output of XOR gate depends on inverter input. That's why it is known as controlled inverter, because this inverter input controls the output of XOR gate. Now from this, what we concluded, when A, here it is, A XOR 0, 0 means inverter is low. When inverter is low, output is same to input, that is A XOR 0 is equal to A. And when inverter is high, that is A XOR 1 will give me A bar. Look at here. That's all about the controlled inverter. Let's move to the next topic. 4-bit adder subtractor or 4-bit 2's complement adder subtractor. Here is the block diagram or logical diagram. In this, we have 4 bits of input A and B. A0, A1, A2, A3, B0, B1, B2, B3. Now, the B input is passes through XOR gate with a AM, that is mode controlled line. Mode input controlled line. Now if I put hand on this, what will I get? If I see only B wala portion, this one, B input, it is similar to controlled inverter, one input and one common input to all, so it will become a controlled inverter. So let's see the working. The operation of both addition and subtraction can be performed by one common binary adder. Now look at this. This is a binary adder, a full adder. Output S naught, carry C naught, which work as a C in 1. Output sum S1, carry C1, which work as a C in 2 for next, and so on. Two inputs A, B, A, B, A, B, A, B. So it is a 4-bit parallel adder or 4-bit binary adder. Now it can be used as a adder subtractor. Such binary circuit can be designed by adding XOR gate with each full adder. Look at here. With each full adder we have used a XOR gate. The mode input controlled line M is connected with the LSB. Here it is. The mode input controlled line is connected to least significant bit, that is first full adder, as C in 0. This control line decides the type of operation, either addition or subtraction. This will decide what we have to perform. We have to perform addition or 2's complement binary subtraction. Let's see. When m is equal to 0, when m is equal to 0, Cin will be 0. Circuit becomes adder. Why? Because just now we have learned from controlled inverter, when inverter is low, that is 0, it gives the same output as input. So for full adders the outputs will be inputs will be A. For first it is A naught, B naught, A1, B1, A2, B2, A3, B3, and C in 0 will be 0. The XOR gate consists of two inputs, to which one is connected to B and other is connected to input M. When M is equal to 0, B XOR 0 is equal to B. Just now we see in controlled inverter. Then full adder add B and A with carry input 0, hence addition operation is performed. Now when we are performing addition operation, S is equal to A plus B will be performed, where S is equal to S3, S2, S1, S0, A is equal to A3, A2, A1, A0, and B is equal to B3, B2, B1, B0. Now when m is equal to 1, circuit become subtractor. Look at this. When m is equal to 1, so C in 0 will also 1, and now B0, B1, B2, B3. So output of all these XOR gate will be 1's complement. Just now we see when inverter input is high, output will be A bar. So here what we get, B bar at the output of each XOR gate. When m is equal to 1, B XOR 1 will be B bar with a carry input 1. M is equal to 1, that is the carry, C in 0, and that is 1, which is nothing but 2's complement operation. Now let's see how it is 2's complement operation. In subtraction, what we do, if I want to subtract A minus B by using 2's complement, first I will take 2's complement of the B. So how we take 2's complement of B? First we take 1's complement of B, or we can say first we pass the input through NOT gate and then we will add binary 1. So here it is, what we take first here, first we take 1's complement or inverter, or we can say passes through NOT gate, that is, so output of each XOR gate when m is equal to 1 is B bar. Here it is B bar. Then we will add binary 1. Here it is Cin is 1. So it becomes binary subtraction by using 2's complement method. So in this case, this circuit performs S is equal to A plus B bar plus 1. This is nothing but a 2's complement subtraction. Therefore, a subtraction operation is performed. That's all about 4-bit binary adder subtractor and controlled inverter and about this chapter as well. Thank you.